Okay, thank you. So I'll be talking about payment schemes from limited information with applications in distributed computing. So it's well known in game theory that the equilibrium often does not ensure the best outcome for the parties involved. And to illustrate this, let's consider an example where we have a buyer and a seller who want to exchange some good for money. And let's suppose that the seller sends over the item to the buyer. Then the best response for the buyer in this case is to simply run away with the money and the item, leaving the seller dissatisfied. But now let's suppose that the parties have some magical treasure box that's able to accept and process payments and release them under certain circumstances. And then let's suppose that the buyer, before engaging in the transaction, makes a deposit to this treasure box, and that this deposit is sufficiently large. Then when the seller sends over the item, their best response will be to send the money so they can recover their deposit. And so the question that we ask in this work is whether or not we can use payments in a sort of, if we can design a generic mechanism that uses payments to incentivize behavior in arbitrary games with arbitrary intended behaviors. Of course, using payments in such a way to incentivize a certain behavior is not a new thing. So in economics, it's known as a deposit refund system. And for instance, in Denmark, if you want to purchase a bottle, you have to make a deposit that you only recover if you properly recycle the bottle afterwards. And similar mechanisms are also used for other consumer goods such as batteries or cars or whatnot. And also similar systems have been proposed for ensuring compliance with international environmental agreements. In mechanism design, there's also a lot of different mechanisms that use payments in sort of various different ways to incentivize certain behavior. I won't really go into detail with this, but it's just to say that it's very ubiquitous with these payments. And finally, in distributed computing, there's also a lot of practical applications, mostly implemented on a blockchain, using smart contracts in various different ways to incentivize certain behavior from the parties. However, none of this work sort of treats the issue of using payments in a generic way that allows for plug and play with an arbitrary game and an arbitrary intended behavior. So that's the question that we ask in this work. And our results are as follows. So first of all, we show that finding an optimal payment scheme is equivalent to linear programming and thus p-complete. Here by optimal, we mean that the size of the payments is minimized. Then we show that we can compute any public function on private inputs with arbitrarily large game theoretic security by using a payment scheme. And I'll go into more details with what this means later in the talk. And finally, we show a lower bound, namely that if we want the payment schemes to be budget balanced, there's a certain bound that the maximum payments must exceed. And this bound matches asymptotically the size of the payments from Theorem 2, showing that the mechanism is optimal in some sense. Okay, so now I'll go through the model. So what we consider are games in extensive form, which are games that are represented as trees, the branches of which are partitioned into a set belonging to each player, and the leaves are labeled with a utility vector. And the game is played by starting at the root, letting the player who owns the corresponding node choose the subtree to recurse into, and then we repeat this process until we reach a leaf and distribute utilities to the players. And we assume that at each branch, there's a unique intended action that we want the players to choose, here marked with a bold action. And sort of intuitively, what we're going to do is just retain the deposit for any party who deviates from this strategy. And clearly, this always works if the payments are sufficiently large and the parties have quasi-linear utility functions. But in order to make the problem non-trivial, we sort of assume that the mechanism is not able to infer exactly how the parties acted during the execution of the game, but that they can only probabilistically infer information about how the parties behaved. So what we assume is we have some finite alphabet of symbols that serve as proxy for how the parties acted. And then to each leaf in the game, we're going to associate a distribution on this alphabet. So here's just one example where we have 3 symbols, sigma 1 through sigma 3, and then we have a distribution on each of the leaves. And then the semantics are as follows. When we reach a leaf, we sample a symbol according to the distribution and output this to the mechanism. And then the mechanism is supposed to process payments based on the symbol that it received. And we call such a structure an information structure. So it's simply a matrix that explicitly for each leaf of the game specifies a distribution on this alphabet. And a payment scheme is then then associates to each of these symbols a vector of payments. So for every symbol, the payment scheme specifies how much utility each of the players is going to lose when this particular symbol is observed. Okay. So our first observation is that if we represent all the utilities as a matrix of the game, then if we add a payment scheme, the expected utility of player pi when terminating in the jth leaf is going to be the I, jth entry of this matrix u minus lambda times phi. And this means that adding a payment scheme amounts to subtracting lambda times phi from the utility matrix, and hence we say the payment scheme implements a given utility matrix E if it satisfies this equation. So now the basic idea is that we want to choose some utility matrix that has a property that we want, and then solve for a lambda in this equation. However, this is not always possible, and in fact we can only implement every single utility matrix if and only if this information structure is left in vertible. And this information structure being left invertible amounts to all of the distributions being distinct. And this means that in some sense we can only do whatever we want if the payment scheme is essentially allowed to observe all actions taken by all the parties. Now, before continuing, I just want to stress how we can implement these payment schemes. So one way you could do it is that after the game is finished, we just hand a bill to each of the parties, and then they're supposed to pay whatever the payment scheme said. However, this only works if the parties are identifiable and can be held accountable after the fact. And we also want our model to apply to settings in which the parties are completely anonymous. So in this case, the robot cat is supposed to represent a blockchain or a smart contract. So in the payment scheme, we're going to have a row corresponding to each of the players. So what we do is that the players, they make a deposit before playing the game that equals the largest payment that they would have made. So they put some money into the smart contract, and then they play the game as normal. A symbol is emitted to the smart contract that then selectively repays the parties based on the payments that it received in the beginning. And note here that a party can actually receive back more money than they initially deposited. Of course, this requires that the payments come from somewhere. And a property that we would in general want our payment schemes to have is that they're budget balanced. So we say that a payment scheme is budget balanced if every column sum is non-negative. And this means that whenever it has to pay back the parties, it received sufficient deposits in the beginning to do so. And if all the column sums are exactly 0, we say it has strong budget balance. However, strong budget balance is a fairly stringent requirement. So in particular, we can only implement a given utility matrix E with strong budget balance if each column sum of U minus E is also 0. And it's not clear in general that we can that there exist matrices E that have properties that we want subject to this condition. So in general, we don't need to implement any utility matrix. We just want to implement some utility matrix that has a property that we want. And in our case, the property that we want is what we call game theoretic security. And we say that a given strategy profile has delta strong game theoretic security if every party who deviates from this strategy profile is going to, on expectation, lose delta utility by doing so. So in effect, delta measures the cost of dishonesty, and we say that if it satisfies this property for a sufficiently large value of delta, then the protocol is secure. Okay, so now just to give an example of the model with the running example that we have. So let's consider the seller. The seller can choose to either send or not send the item. And after sending or not sending the item, the buyer can choose to accept or reject delivery of the item. Here, accepting means that they hand over the money to the seller, and rejecting means that they retain their payment. And let's suppose that X is the transaction cost. This is how much money the buyer is supposed to send to the seller. And let's suppose that the seller values the item at X prime, and that the buyer values the item at Y. Then we're going to get the following set of utilities that we can represent as utility matrix U. And here I've denoted with the bold edges the actions that are best responses for the parties. And as hinted at in the beginning, we see that the only equilibrium in this case is for neither party to engage in the transaction. So now suppose we want to get X strong game theoretic security, meaning that a party who tries to cheat is going to lose as much money as is being transacted. Then we can implement this utility matrix instead, where I've marked with the blue the changes. And so in order for a model to apply, we need some information structure on this game. And let's suppose that in the case of disputes, we have some noisy means of figuring out who were the honest party. And let epsilon be the error rate. Then we're going to get the following information structure, where the top row corresponds to everything being fine and the buyer accepting delivery of the item. Second row corresponding to the buyer cheating, and the last row corresponding to the seller cheating. Then what we want is we want to find a suitable payment scheme that satisfies this equation. And for our setting, there is a solution that we can find using Gaussian elimination, where here the first row corresponds to the payments from the seller, and the last row corresponds to payments by the buyer. So they should, before engaging in this transaction, they should make a deposit that equals the largest value in their corresponding row. And to make this more concrete, let's suppose that the buyer and the seller are transacting some item for $100, and that this item has a value of $50 to the buyer, to the seller, sorry, and that the error rate is 0.1. Then the buyer must make a deposit of size $225, while the seller must make a deposit of size $57. And if the parties do this, then we will get $100 strong game theoretic secure commerce, meaning that a party who tries to cheat the other party is going to, on expectation, lose $100. And in general, what we want to do is we want to minimize the size of these deposits. And we observed that this is equivalent to linear programming under log space reductions. So this shows the first theorem that finding an optimal payment scheme is p-complete. We also show a lower bound, namely that if the payment schemes are to be budget balanced, then if we want to get delta strong game theoretic security, we must have a maximum payment that's no smaller than omega of 1 plus delta square root n over s. Okay. So as a last thing, I want to illustrate the model on a slightly more involved example than the one we just had, namely of multi-party computation. So in multi-party computation, so this is, I'm going to very informally go through this because there's a lot of technical issues with some of the definitions. But let's suppose we have a group of parties who want to compute some public function on private inputs. And they want to do so in a way that's as good as having a trusted third party, but without actually having the trusted third party. So they run some interactive protocol that specifies how they should exchange messages. And there's various notions of security for MPC, where the sort of most basic notion of security is that of semi-honest security, where the protocol execution is going to leak nothing more about the inputs of the other parties than that which could have been gathered from the function output itself, assuming that all the parties adhere to the protocol description. There's also a more stringent notion of security called active security, where the same holds true, even if the parties are allowed to arbitrarily deviate from the protocol description. And of course, active security is stronger than semi-honest security, but they're also orders of magnitude more expensive to run in practice. So sort of an intermediate notion of security called covert security has been proposed, where parties are allowed to cheat but are caught with some constant probability epsilon. And here the intuition is that if we have competing firms that want to do some joint computation on shared data, they don't want to risk being caught because it could tarnish their reputation. But let's suppose we want to do this for anonymous parties, then they might not care about their reputation in any meaningful way. So we want to do so using payments instead. So now we're going to get, from the covert security functionality, we're going to get a game where each party can choose to cheat, and if they're successful in cheating, they will learn the inputs of all the other parties. If they are not successful in cheating, they're going to get caught, but nothing happens, so everyone gets 0 utility. They can also choose to abort, or they can choose to give their input truthfully. And we say that if all the parties give their inputs truthfully, everyone gets 1 utility. And if I get your inputs, I'm going to get U plus utility. And if someone gets my inputs, I'm going to get U minus utility. So this is a game we can write up. And if we take these moves by nature and we sort of merge them into one node, then we can get an information structure on this by the definition of the covert secure functionality, which is the following, where the top row corresponds to everything being fine. Next row corresponds to first party aborting. Third row corresponds to first party cheating, and so on. So we get this large matrix. And let's suppose we want to get delta strong game theoretic security for some value of delta. Then we can choose the following utility matrix. So here, if I cheat, I'm going to, on expectation, lose delta utility. Everyone else gets 0 utility. And if everything goes right, then everyone gets 1 utility. So this matrix has delta plus 1 strong game theoretic security for the honest actions. And so in order to get this, note that this information structure is actually full rank. So we can find the payments by using this equation. And we have a row corresponding to each of the parties where U plus delta over epsilon is the largest value in each row. So this is the deposit that each player should make. And this shows theorem 2, namely that any function can be computed with delta strong game theoretic security by taking one of these covert secure protocols with parameter epsilon and augmenting it with payments where each agent pays on the order of 1 plus delta over epsilon. And this is optimal by theorem 3. So to summarize, we gave a model of games with information structures and showed how information structures can be used generically to incentivize behavior using payments. And instantiating the payments is p-complete. And finally, we applied the model to secure commerce and secure MPC, for which we showed that the size of the payments is optimal. Thank you very much.
All right, and we can take questions. Go ahead.
Is theorem 3 tight? And actually, how do you, is it a duality type argument? Or how do you do it?
So it's you consider the so it's based on the bounds on the matrix norms.
Oh, okay. And then is it tight? Do you know if it is? Can you construct games for which actually is the asymptotic limit?
So asymptotically, it's tight for these games, but I think it's not tight in general if you want to get the concrete values.
And actually, I have a quick question. So if I understood correctly, the results you showed that applied to MPC assumed that epsilon was kind of exogenous, that it wasn't the case that once everyone knows the system, then whatever thing you're using to detect or the signal structure can't change as a result of people's actions.
Mm.
So I'm wondering, so like in the buyer-seller example you had, I'm wondering whether that assumption is right for that setting, and I'm wondering if you have any thoughts on what would be different if once everyone knows the signal structure, they can change what they do, which would change the signal structure.
So for the MPC case, it's the knowing the signal structure. So here all the parameters are public, and here it's not possible to change. But I think in the other, so that would depend on how you construct this means of figuring out who's honest. And I think so. There are some proposed solutions, and my intuition is that it probably won't change that much. But there's for sure some games where you could think of where knowing how this information structure looks actually changes the incentives in the game. But I think for these two examples here, this is not the case.
Cool. All right, and that's it. So we can thank all the speakers, and thank you very much.